Okay, hi guys. So from this lecture we'll be taking on new type of reaction called nucleophilic aromatic substitution. Okay, so let me first write down the heading. So from now we'll be talking about nucleophilic aromatic substitution. Okay, so let us say we have benzene and it is substituted with Cl and a NO2 group. NO2 group is obviously minus M group, and first we are reacting it with OH minus, whose pH is actually 14. Okay, and at 160 degrees Celsius, and then second we'll be treating it with acidic medium. So what we find out is we get something like this with NO2 group attached. Okay, if we have a simple benzene ring and we get some nucleophile in it, we see no reaction happening. Okay, if we see something like this, NO2 here and NO2 here, so first we give it a basic medium whose pH is 10, and then obviously we have 100 degrees Celsius, and then obviously we have H plus or acidic medium introduced into the reaction mixture. So we get something like this, OH, NO2 and NO2. Okay, fourth example we have something like this. We have Cl here, NO2 at ortho and para position, and again we react. This time we just require water to be passed on into the reaction mixture, no need to have even basic medium, and we find out that we have OH in place of Cl, and rest positions of nitro group remains the same. Now let us talk about the mechanism. Okay, so as you can see, more the number of NO2 in attached to the chlorobenzene, lesser is the pH of the basic medium we required. Right, when there was only one minus M or NO2 group attached, we needed pH of 14. Then we had two NO2 groups, we needed pH of 10, and now we have three NO2s, we don't even need a basic medium. Now let us talk about the mechanism as to how this happens. So we have a Cl group and OH minus group is introduced into the reaction mixture. So what actually happens is we get something like, let me draw the bonds, double bonds. So we have something like this, and we get introduced OH group in the compound, and we get negative charge here. Okay, as OH minus is attacking this benzene ring, specifically at this position. Why? Because it is delta plus at this carbon position. Okay, so it is natural for a nucleophile to attack on a positively charged carbocation. Okay, and we get something like this. Now what happens is negative bond actually forms a bond with this carbon atom, thereby Cl as Cl minus, as Cl would go out as Cl minus, withdrawing its bond pairs from this carbon atom, and this is actually known as Mischer-Hammer complex. This is known as Mischer-Hammer complex. Okay, in which we have a carbanion as the intermediate, and this carbanion as the intermediate would result into aromatic nucleophilic aromatic substitution. Next we will have something like phenol ring here or phenol group here, and the Cl minus would be produced. Okay, now so as to stop further OH minus taking away this H plus from the OH group or the phenol ring, we introduced acidic medium. Okay, in acidic medium, Cl minus would attack on Cl minus will attack on H plus and will form Cl minus, HCl. Okay, and please remember that alcohols and ethers are stable in basic medium, hence they are not stable in acidic medium. So we would see their reaction in acidic medium, not in basic medium. Okay, so what is in the presence of NO2, what actually happens is, if we had NO2 attached at the para position, we would get something like this, and let's actually make this product NO2. Okay, and then we have something like Cl and OH attached here with negative charge here, and we have, so what will happen is this will go into something like this and form a compound like this with double bond here, and obviously O will also take its negative charge here. Okay, so this actually brings in more stability as minus M group is attached and we have a carbon ion in the cyclohexane ring. Hence it will increase the stability or increase the stability of RDS, thereby taking the reaction into the forward direction. Okay, hence we saw that more the minus M group attached to the benzene ring, more would be the rate of reaction towards nucleophilic substitution reaction as the RDS intermediate gets more and more stabilized. Okay, so please remember that the RDS in this step was the formation of carbon ion, or I'm just drawing it again, Cl and OH. So please remember that you can also say that OH could have attacked on this carbon atom, as this would be a good leaving group and this is a slightly bad leaving group than NO2. But this is not the case. And why this is not the case? We are just not concerned about the leaving group in the RDS. The RDS just talks about the stability of the carbon ion. Okay, hence no leaving group is seen for comparing rate of reaction in nucleophilic aromatic substitution. Okay, so let us talk about the characteristic of this reaction. Okay, so we have first characteristic as nucleophilic substitution reaction follows AE mechanism, means first addition and then elimination. Okay, so addition then elimination. Okay, let me write it down here, addition then elimination. Okay, second point is rate is directly proportional to the concentration of halide and the concentration of OH minus. Okay, hence the order for this reaction is 2 and it is a bimolecular reaction. Okay, let us see the third characteristic. So carbon ion is an intermediate. Carbon ion is the intermediate. Okay, let us see the fourth point, wherein we need to compare the rate of nucleophilic substitution reaction in these compounds. Okay, so what is the rate of reaction in these compounds? Obviously it is of the order this, because the incoming OH minus group would be seeing how much is the carbon atom having partial positive charge. As you can see, the electronegativity order is of the decreasing order, hence the rate of nucleophilic substitution reaction would also be in the decreasing order, because this carbon atom would be having the highest partial positive charge. Okay, because of a strong minus I effect. Okay, so let us see one more example. Suppose we have, so actually when we saw the electrophilic substitution reaction in NO2, we saw that NO2 would be metal directing for electrophilic substitution reaction, and in this case NO2 would be ortho and para directing in case of nucleophilic substitution reaction. Okay, because the incoming nucleophile will see which carbon atom which does have the maximum positive character. Okay, because of the minus M group called NO2. Okay, so let us see some example over here. We have something like this group NO2, this is minus M group obviously, and 2 Br attached here. Okay, and the incoming nucleophile will see the maximum positive charge would be on this and this carbon atoms. Okay, and on the top of it, on this carbon atom, it is also having minus I effect because of the Br group, hence OH will prefer to be attached at this position, and we would have something like positive charge or rather negative charge here. Okay, so this would be stabilized with the conjugating structure which can form with this pi bond, and this pi bond can shift in the and form a double bond between nitrogen atom and this carbon atom. So then we'll find something like, again we would get that Br is actually removed from the reaction due to the presence of H plus introduced into the reaction mixture, and then this again restores the benzene ring, as this negative charge would then again make the double bond between itself and this carbon atom. Okay, so we'll get something like this structure. Okay, Br was here and NO2 is here. So this will be the product in this reaction. Okay, so this brings us to the end of this lecture. In the next lecture we'll be seeing some more examples and concepts on nucleophilic substitution reaction. So till then, good luck and goodbye.